make sure that the volume control is working, so all's good. And the streaming is up. Okay, very good. Okay, it's good to double check. All right, so let's go take a look at these questions. Now, these are the questions from last semester, so it would be totally easy for you guys to answer this question. Is that the reason why you were kind of?
No. I was just thinking if I did policy hash because they were smoking something.
or C she, shebang. You know, the pound exclamation point is shebang. Yep. All right. So question number 1 is super easy as far as if you guys are to do this one. Okay. So let's take a look at the question and let me explain why it is easy. For many operations, it is important to increment or decrement a register by 1. For example, A++ or A minus, A being a register. More importantly, it is important not to change the flags register, nor to access memory like an immediate operand of LDI. So let's call the new instruction inc, which we have, or dec, which we have, for incrementing and decrementing a register. Assuming we would want to utilize the ALU for increment and decrement and not to have individual adders for each register, and the above criteria are to be met. Explain why such an opcode cannot be implemented using the current architecture. Now, this is before I made changes to the original the processor architecture. So your answer should include a statement of what is needed to be done or what needs to be done in terms of component port connectivity, and also how the current architecture is not supporting it. Okay. So obviously, I cannot ask the same question because the processor that we have been using obviously has all the necessary features already. Because of this particular question from last semester, I added the features, so that we have increment and decrement. So for this semester, there are many other things that we cannot do. Okay, one is to push the value of a particular memory content onto the stack. That's one thing that we cannot do. We cannot add a constant, okay, other than 1 to a register. So those things, cannot possibly be done. So you might be asked to say, okay, this is your current architecture. This is what I want to do. Tell me why we cannot do it. Regardless of how we program the microcode, it is still not possible. Okay. So let me give you an example. So the example, I got the other thing working here, so this is good. So I might ask you and say, if I were to use this instruction, add I, we specify a register, and then we specify immediate constant. The effect of this instruction that I'm proposing is just going to do this. Okay, I'm going to use / to separate the C description from the actual description here. So I just want this to be x plus equal to asterisk PC plus plus. In other words, whatever the opcode is, right after the opcode is a byte. That byte specifies how much I want to add to the register XX, which is one of the 4 registers. Okay? So now the question is, why can't I implement this instruction now with the current architecture, no matter how I specify the microcode in the ROM? Why is this instruction impossible to implement? So how would you start to think about this particular question and answer it? Where do you start? Remember, the test is open book, open notes, just like the previous one. So what do you need to bring, and how do you get started with this one? Yes, go ahead.
Does it have something to do with the fact that we're only incrementing the program counter one at a time, and you can't force that anymore?
Not exactly, because I can separate these two into 2 different operations. So so this is, I'm going to keep it the way it is here, but I can give you an alternative way to express this. I can say x plus equal to star PC, and then we have plus plus PC on the next line. I can break it up. Okay, so now we are not adding things at the same time on the same line, but I would still say this is not possible. Why is it not possible? Yep.
Is it because it's not possible to retrieve the value of a program counter?
No, we have a way to do that because we have LDI. So LDI does about the same thing. Okay, so that's probably a good thing to review. Is what does the LDI instruction do? And okay, so let's go back and look at the LDI instruction, which we know for sure works. Okay, we have the LDI instruction and it works. So the LDI instruction is really just saying register X equals to whatever the program counter points to. And then we increment the program counter so that we skip that location in memory that we just kind of copy into the register. We have that instruction. So we do have a way to use the program counter to point to a location and then put that into a register. But we do not have a way to perform the first instruction. What is the difference? Yeah, go ahead. Okay, so it's all right. So now, so the first question is, how do we implement the LDI instruction? That's the first question. How do we get this done first? Okay, so when you look at this one, how are we doing it right now? Which is a part of your studying. Okay, so to study for this class is really to look into the implementation of the instructions in terms of microcode, how it connects the multiple components inside the processor to form the correct pathway to get it done. Question? Answer? Go ahead.
We use the load and we increment after.
Okay. All right, so this is probably a good time to kind of mention how we can, the various ways to study for this class. Depending on whether you are a visual person or not, okay, so visual people may prefer one way, and then people who are more abstract may prefer the other way. So it's up to you. So the first thing we do is, for visual person, this is your starting point. Okay? So your starting point is this, and you can always print it out and bring it with you. Okay? Very good. You might want to also print out the register bank and also the ALU on separate sheets because they can come in handy as well. Now, sometimes you might want to bring several copies because you might mark up one of those for one particular question, include it as a part of your answer. So if you have multiple copies, then you can say, oh, okay, for the next question, I can use the other sheet.
And there are 5 questions, right?
There are 5 questions, yep.
Okay.
4 points to each one.
So make 4 more copies, essentially.
Well, I mean, it depends on whether you feel that there will be a need of that or not.
Worst case scenario is scratch paper. It's scratch paper.
Right. Okay, so getting back to the first instruction. In other words, what we are trying to do now is kind of just look at an existing instruction like this one. How is it done? Or first of all, is it possible? Can we do this? The one that is in green circle. Is that okay? All right, so how do we know this instruction is possible? Even if the ROM is empty, there's nothing specified, how do we know this instruction is actually possible? All right, so what do we want to do? We are going to bring in, what is this part representing? What is this part representing? It's a dereference, okay? And it is accessing what when we are dereferencing?
The stack, or not the stack, the
No? RAM, very good. Okay, so every time we see the asterisk, it means we are accessing RAM. We may be writing, we might be reading, but it has something to do with RAM. Now this time we have the asterisk symbol on the right-hand side, which means are we reading from RAM or are we writing to RAM? We're reading from RAM. Very good. Okay. So whatever we read from RAM, we want to put it into a register. We are overwriting a register. We are updating a register with something that we are reading from RAM. So the question is there a pathway to do this? That's the question. Okay. So you go back to the picture. You go back to the processor architecture, which hopefully you have a printout of, and you just go like, okay, this is the output of RAM, the data port. And obviously, since yours is going to be on a piece of paper, you cannot just click it and have it highlight. But we have done this several times already. So you follow this thick line, it goes into this mux. This is the port to update something in the register bank. Okay? So you go like, okay, so it seems like there is a path from the output or the data port of RAM into the input port of the register bank. Is that okay? Cool. So that means the first part can be done. We now know that this part can be done. The second part is, can we increment the program counter after we take something from RAM? That's the second question. The program counter is down here. This is our program counter. And you go, can we increment the program counter, but after we use it to tell us which part of RAM to access? First question first. Can the program counter be used to specify the address port of RAM? Okay, well, let's look at this line here, and if we need that to go to the address port, which is here, so you can see that they are separated by a mux, which means it is connectable. Okay, we can make that connection, which is good. Second thing is we have to increment the program counter. Can we increment the program counter unconditionally? In other words, I'm going to add one to the program counter regardless of the states of the flags and whatnot. Can we do that? Well, we have the incrementing mechanism here, which has a path through a mux back to the input of the program counter. So now the question is, can we specify a 1 here as my carry in so that I'm really just adding 1 to the program counter? This is the OR. We have PC Inc. and then we have address mux. If at least one of these is a 1, we are good. Well, is address mux going to be a 1? It is going to be a 1. Because in order to connect the output of the program counter register to the address pin, in order to make this connection, this is 0. This is input 0. This is input 1. Which means to make that connection, ADDR mux, the address mux, has to be a 1 already. If address mux is a 1, this is a 1 coming into an OR gate. The output of the OR gate has to be a 1. So indeed, we have a way to perform these two operations with LDI. So now we have to apply the same kind of analysis to the instruction that I'm proposing, which is this one here. And then we say, how come this one is not possible? How come I cannot do about the same thing to specify a constant to add to a register in memory so that we can have ADDI or add immediate to a particular register? How come this one is not possible? Well, the problem has to do with this operation here. The first one is a problem already. We can get something out of RAM, not a problem. Okay, because this star PC part is the same as this star PC part. That is not a problem. The question is, how do we get this into the ALU directly so that we can add? Is that okay? So now the analysis is go here. We go to the ALU, which is the only component that is capable of adding arbitrary values. The other ones can do increments, but they cannot just say, oh, add whatever number. I want to add 1/6 in hexadecimal. It cannot happen. So now we look at the inputs to the ALU. This input to the ALU has to come from this particular demux. This particular demux comes from the output of the register bank. Okay, it has to come from one of the registers. Cannot come from the data port of RAM. Okay, maybe the other one will. Look at this one here. This one looks like we got a slight chance because it's coming in through a mux. Okay, which means we have 2 sources in order to specify 2 sources to specify the second input to the ALU. We look at the first one. Okay, input 0. This one goes through a demux to the register bank. Okay, this is a dead end. The other one connects to a constant. 0, 1 is a constant. We don't have a path. There's just no path to connect the output, the data port of RAM, directly to one of the 2 inputs of the ALU. That would be your answer. So it doesn't matter what you do, how you specify the microcode slices, there's just no way to do it. So is that okay? Are there any questions about the answer to that particular question? Yep.
The actual reasoning you went through, like going through the diagram to actually figure that out.
Yeah.
Would we have to include that in the answer in some way, or
Yes.
is it enough to? What are you looking for as the answer, as a complete answer, is what I'm
You basically state that there's no such path possible.
But we don't have to prove that. We can just say that that's that and refer to
That
it.
is correct.
Okay.
Yep. Yep. Yeah, because you cannot. Yeah. If the path is there, you can just specify. Okay, it goes through this component, this component, this component, this component. But if it's absent, you just have to say it does not. There's no way to connect this to this,
Gotcha.
which is what is needed to perform the proposed operation. Okay, that's a good question. Any other questions about number 1? So questions like these require you to really understand the architecture of the processor, the current way it is implemented. Yep.
So let's just say you're looking for a function, you can use it in your architecture. How would the answer be specifically? Like you just tell what components of the processor are being used?
You have to say, in this particular case, you have to specify that the addition part, this part here, the plus equal to, can only be done using the ALU. Okay? So you identify the ALU is used. Out of the 2 inputs of the ALU, one can take the input only from a register bank. The other one can take its input from either a constant or through the register bank. So there's no way to connect the data port of RAM directly to one of the inputs of the ALU, and as a result, the operation cannot be implemented. So that is basically what I'll be expecting from your answer. Is that okay? All right. So getting back to the other test questions. The toy processor has some opcodes that are not particularly useful. So this one is kind of tricky because I'm kind of chaining the second question sort of to the first one. For example, AND AA updates the flags register, which is kind of useful, but otherwise it does not change any register, which means the instruction is not particularly useful. OR AA is the same thing. So likewise, sub AA clears the value of a register and is guaranteed to set up the flags register to a certain state. The same thing goes for compare AA. So one of these is not needed, okay? Except compare AA does not affect register A. Okay, so I can see some questions. So are there any questions about just this paragraph, which is just a setup for the actual question itself? Can everybody see why AND AA is not particularly useful, other than saying, hey, is A 0 or not? Yep.
Because it doesn't do anything with the flags. It's just.
It does do something to the flags, but we already know it's not going to do much. Or what it does to the flags is already known, except for the Z flag. The Z flag is the only one that changes depending on the value of A. Because if you look at this AND AA instruction, it's performing a bitwise AND of A to itself, which means if A is 0, AND AA is guaranteed to set the Z flag, which is actually useful because many times we just want to know is A 0 or not. But other than that, it's not particularly useful. Is that okay? So the same thing applies to OR AA, which is because if OR AA and AND AA are doing exactly the same thing, okay, because it is the same register. And then we have subtract A from A, which is actually useful because we can use it to reset the value of a particular register. But compare AA is useless because it doesn't update the register. And we already know it's going to set the 0 flag because we're comparing A to A, which is kind of useless. So this means we can steal certain opcodes from these particular instructions. So we can just say, oh, okay, we can just take the opcode of compare and AA, and BB, and CC, and DD to do something else. To implement more useful instructions like increment and decrement. So here we say suggest the opcode that you would steal from, in the existing instructions. To implement increment XX and increment YY, you will need to steal 8 opcodes altogether to arrange these in 2 groups. Okay, so is the question itself understood or not? Okay, and how would you answer that question? Because I want you to specify exactly, what opcode would correspond to increment A, increment B, increment C, and increment D. Go ahead.
So the 2 different groups mean 2 different instructions, or the 2 4-bit to make 1 8-bit command? This is arranged in 2 groups. Does that mean 2 separate?
Yeah, 2 groups. Yep. 2 groups, because one group is increment A, B, C, D, and then the second group is decrement A, B, C, D.
Oh, okay, you're right. Okay.
So what the question really is asking, if I were to clarify, it is basically asking, if I want to implement A, increment B, increment C, increment D, what would be the opcode for these? And then we have decrement A, decrement B, decrement C, decrement D. What would be the opcode of those 4?
Okay.
Yep. So the best answer is the actual hexadecimal opcode, which you have to kind of do some lookup. So to look up the opcode, this is also kind of reviewing stuff that you might want to print before the day of the exam. Because when you go to the shared folder, which is, I can't do a left click here. It's okay. Nope. There we go. Okay, so when we go to the share folder, go to the processor subfolder, there's one spreadsheet that you might find particularly useful, which is the opcode table. So the opcode table tells you everything that we have already used. So in this case, when we look at AND AA, so we are looking at AND here, okay? So we are looking at 1100, 1100XXYY. So when we switch back to the pattern that we are looking at here, this one would be 1100, and then 000, because this is A and this is A. Okay. Next one is 1100, 0101. This is B and this is B. 1100, 1010, 1100, 1111. Okay, this is assuming that we're stealing from AND. Okay, steal from the instruction of AND. And then for decrement, we can steal from OR. Steal from OR. So about the same thing. You just have to figure out the bit pattern for the OR instruction, which is 1101 XXYY. Okay, so in this case, we have 1101 0000 1101 0101 1101 1010. Oh, okay, I see. No wonder you guys were looking at me go like, what? Okay. And then 1101 1111. There we go. So that would be the answer to that question. Yep.
In the instructions, weren't you saying that you don't need both and or, but it is useful to be able to compare and AA to check 0?
Right.
So, since you said that was useful, my question is mostly, if in the instructions you say that's useful, why would we know that we should remove both sets of the instructions?
So you have choices. You can also steal from the other ones. You can steal from compare. So compare AA, compare BB, compare CC, compare DD. You can steal from those 2.
Okay.
Yep.
So we could arrange that.
Yeah, it's your choice.
Okay.
Because even though they're useful, it's not like we cannot do it otherwise. It is just that we have to use up something else. We have to use another register, and it's kind of cumbersome. So it depends on what is considered a fair trade for the features that we are getting.
Gotcha.
All right. So is that okay? Does everybody understand, the answer to question number 2? If the answer to this question is basically what I have down here. So this is for question number 2. I'm just gonna label as such. Okay. Yep.
What would be some common answers that are wrong but are decent answers? What would be someone that had the train of thought that makes sense but isn't the answer you're looking for?
I'm trying to think of. That's actually a really tough question to ask me. What are the ways to get it wrong? Okay, suggest the opcode that you would steal from existing instructions. So maybe someone would say, oh, we can steal from jump, okay, JMP without the I. Well, that would not be good. Those would not be good instructions to steal from, because we actually do need those, jump instructions. Yep.
So I just want to clarify what you mean by steal is since the opcodes don't do anything, you want to reinterpret.
Yep, reinterpreting, correct. Yep. In other words, if we had the instruction of add A with A, it would have exactly the same code, okay? It would have exactly the same opcode or the same binary representation. Oh, okay, gotta switch back. Okay, so it gotta have the same opcode. It's gonna have the same opcode as, in our case, increment A. So that means, it can only do one, it cannot do both at the same time. So we have to make a choice here. So my choice is, oh, we don't need, not add, this is actually and, sorry. So my choice is to get rid of the and AA, because I would prefer to reuse the opcode to implement increment. Okay, so is that okay so far? Okay. Question number 3. The current toy processor architecture lacks the support to supply a constant value to the ALU that is not from RAM. Part of the change is already proposed as follows. In other words, I give you something here, and there's a question mark here. Your job is to figure out how to specify the tunnel, which is this one here, marked as a question mark, so that the following criteria are satisfied. No need to add any bits to the width of the ROM, so I don't want to, okay, let me specify what I mean by that. By that, I meant I don't want to change the format of the ROM. Okay, the ROM currently has a width of 26 bits. I don't want to change that. I'm not going to add, I don't want to add any additional bits to do this. The second criterion is to maintain the operation of all existing opcodes without microcode changes. This means, with all the opcodes that we already have, okay, in the opcode table, in here, I don't want to have to change anything here. Everything that is currently supported would still be supported by the existing microcode slices. Okay, minimal changes. And then the third part has provision to implement the increment and decrement register opcodes. So that means, I have to somehow factor that in so that, using this tunnel, sometimes I would use a constant of 0, 1 to supply into, and other times I can still use a register to supply into. So your answer should state the expression that connects to the select input pin of the new mux connecting to into of the ALU. In other words, what you're going to do is to specify this equation. What equation should go into that tunnel so that we can get the job done. Okay. And then 2 is explain why your expression works to maintain microcode of existing opcodes. In other words, from the perspective of current opcodes, how is this change not affecting them? So all the opcodes that we already have, whatever you specify here is not going to change the way the current opcodes, the ones that we already have, would function. Now, to this particular class is already done. Okay, if you look at the current computer architecture, it already has that tunnel specified. So when we go up here, you can see it is called FC, but then FC is computed up here. So the correct answer is to look at the register output 1 demux and also ALU enable. Bring those two into a NAND, and then the output is the answer. It's a NAND. It's a 2-input NAND. So now okay. So first of all, you have to come up with this. So the further question is, how do you come up with this?
We look at our printout and see what's there.
Yep. So you will have to know the microcode of all the current instructions first, okay, or at least have a good understanding of how they make connections. Okay. So one way to do this analysis, okay, I switch back to this slide because this is what you'll be given with, or this is what students were given with in spring. So you look at this and say, all the previous instructions do not really have this part, right? This is a new instruction. This is added because of that. In other words, okay, let me see if I can do something that will make this kind of helpful. I think I might be able to do this. It's the first time to doing everything. This is the first time I'm going to do this. So I can print it out as a bitmap. Export main as a PNG. Printer view. Okay. And then we'll export it to processor.png. And then we'll see if I can import it into here. There we go. Okay. Does it look like there's an option here to paste into here? Oh, this is not even on the same computer. Darn it. Yeah, I'm trying to find a way to highlight pathways here on the tablet. I have to put it onto. You can open PDFs, but that's about all you can open. Yeah, I will have to do that, but there's no actual connectivity to copy and paste between these two. Okay, I know how to do it. Okay, just give me a second here. So we're gonna have to export this one as PDF, and then push it back on the web. Download as PDF, and then put it back into the share folder. Save. Yeah, the tablet can open my share folder through Google Documents. Okay, so that is that, and then we will add it back to here. There we go. And then on this side, there's no quick and easy way. I can show you how it's done, just in case someone is interested. Let's see. Look into here. Okay, import PDF as new notebook. That's the only way to bring a PDF in. So now I can go to my drive, go to my same account, go to 310, go to shared, go to exam 2, and here's my PDF. Select. Okay. And it wants a different resolution too. So I don't think this resolution would work out. So it wants to use a different resolution because it's a letter-sized paper. This will work. And then and save, create and open. Import all pages. Yeah, sure. We only need a page, but we'll open all, save all pages anyway. Doesn't take that long. Yay. So now we just have to flip to the right page. There we go. Cool. Okay, so now we can I can actually highlight stuff. Okay, so we'll highlight stuff here. All right, so that looks kind of small. Can I zoom in, make it larger? Well, zoom is enabled, but how do I actually do the zoom? I tried a gesture already, huh?
Did you give them her one above double tap? Just double tap.
Nope. Okay, one more time. Try. I don't think that's just adding a new page, which is not what I want. Can I zoom here? Nope, it doesn't. Can you guys see it from here? I know it's kind of difficult to see it. It's okay? All right. Okay, so so the bottom line is this mux was not This mux was not there before. Okay? In other words, before this change, the processor had a straight connection, the red line that is connecting. Is that okay? So now the question is, I want that connection to be quote-unquote default. For all the existing instructions, that's the default way of connecting. That's the question. How do we make sure that it is compatible with all the existing instructions? And then for some new instructions, we want that to connect to the other one. Okay, I'm going to use a different color. Okay, let's say green. And say for certain new instructions, we want a green connection. Is that okay? Let's see if this works. Nope, I can't zoom here either. Okay, that is kind of frustrating. So, is that okay? So now the question is, I need some kind of equation. Okay. So let's go back to the red line here. So I need something to be red, and you can also see the select pin. Okay, this is the selection here, and this is the red line is when the select pin is a 0. The green line is when the select pin is a 1. Okay, so the red, oops, darn it, get back. Okay, so the red line is when it is 0. And then the green line is when it is a 1. But we want the same expression on the other side. So are we doing okay so far with the analysis up to here? So I want the same expression. I want the expression to evaluate to 0 for all the existing instructions. Everything that is not increment or decrement, I want it to be 0. And then for all the other instructions, for the new instructions, the increment and decrement, I want that expression to evaluate to 1. So now the question is, okay, what do we use for this purpose? So think about increment and decrement, okay? And you say, all right, so with a normal instruction that makes use of the ALU, what is the pattern of using it? And then what is usually not the case, and then we'll just borrow a particular bit pattern to do this. Okay. Any questions? Any ideas? Okay, first of all, do you think the ALU is important? ALU enable is important in the determination of this whole thing? Seems kind of important to me. And then the second thing is, what is the red line connecting to? Right. Okay. Very good. Okay. So let's follow the red line. So the red line goes down here, right? And it goes into this demux. And what is that demux going to on the other side? It goes to output 1 of the register bank, right? So that means the red line is useful only when we make use of output register output 1. Is that making any sense? Okay. Oops. It's okay. Maybe I clicked on something. Maybe not. I think I clicked. My palm touched the back button on the bezel, so that's why it keeps going back. So I have to kind of make sure I don't touch that. Okay. So we know that output 1 is important, and how can we know whether output 1 is even in use or not? Output 1 doesn't have its own enable. Okay, output 0 has its enable, which is this one here. Output 1 has no enable, but it does have a demux. Okay, so we look at this demux here, and we say, okay, so where can output 1 of the register bank go other than the ALU? Where's the other path going? In other words, we are asking, where is this path going? There's a second path here. Well, wherever it is going, it is not the ALU. Is that okay? Is that okay? All right. So we just write down here. Okay, I did it again. my palm clicked the back button. Okay, I just have to kind of write in a way that it doesn't do it. Okay, so we say that when our register output 1 demux, when it is a 0, we can borrow that. Okay, when it is a 0, we want the green to be to do this. Okay, so let me put this over here. When register output 1 demux is a 0, that's a clue. Okay, this is something that we can borrow as a bit pattern and say, oh, since register output 1 is not connecting to the ALU, now the 0, 1 constant can connect to the ALU. Is that okay? Which also means when register output 1 demux is a 1, we want the tunnel in question to be a 0. Is that okay? But by itself, that's not sufficient, because this may turn on it may turn that switch when we are not ready for it. Okay, so we need one more clue. In other words, we need to say, yep, turn it this way now. So now you have to kind of use your own documentation, use your own printout, and basically find out where this is going. Okay, because wherever that is going, it's gonna it's gonna help us decide, oh, when it's going in this direction and that thing is not active, that's when we want this thing to switch to the constant. So now we switch back to Logisim here, and we are basically following this connection here. So let me click that and have it highlighted. Where is that going to? Ah, it's going to a multiplexer that connects to the address bus. When we're incrementing a register, do you think that we need the address bus for anything? Probably not. Okay. So maybe we can use address mux as a clue and say, Most of the time when we connect this way, the address mux is going to be a 0 in order to make use of register output 1 to control the address bus. So when we choose register output 1 to hook up to input 0 of this mux, and yet we are having the address mux to hook up the other way, that might be a clue to say that, hey, we are not doing anything with the address bus with register output 1. In fact, we are not even using output 1 from the register bank. Okay. So now we take this and go like, when address mux is 0, is 1, that would be a good determination, or good way to determine the other one. Okay. Let's see, I mean, it is a 0 or 1. Okay, switching back and forth here. And also, I'm going to cheat here. It is using ALU enable. Okay. So it's using ALU enable as a part of the equation, because when ALU enable is 0, which means we are not using the ALU, what is the default state? What is FC when ALU enable is a 0? This is a NAND gate, by the way. It's going to be a 1, which means it switches to the green line when we are not using the ALU. Does it really matter if we are not using the ALU that it switches to the constant of 0, 1? In other words, when the ALU is not enabled, it's going to feed 0, 1 to in2. Would that affect any existing instructions? It would not, right? It should not affect any instructions, because if the ALU is disabled, it's not doing anything. It is just absolutely just not doing anything. Okay, so that is your answer of why this design, or the way that we set up this equation, is not going to affect any existing instructions. But why would it help to do what we need to do? When ALU is enabled, which is a 1, and register output 1 demux is also a 1, which means the output register 1 here is sending. It's also so confused here. We also want that demux to be okay. So we want this demux to be a 0. We want this line to be a 0. To specify to use a constant here. But that makes sense, because if this demux is sending the output of if it's sending the output 1 of the register bank somewhere other than the direction of the ALU, that's a good indication that we want to use a constant of 0. So that's why we choose this equation of using RO register output 1 demux and ALUEN as the input to a NAND gate, and then the output is used to control this mux. Is that okay or not? Yep.
So if ALUN is 0, which effectively makes the ALU not do anything, then in that case, in the case where it's 0, can we ignore disregard the value of RO1 DMX? Because if you're not adding with the ALU, then there's no reason to pay attention to what the demultiplexer is sending, or the multiplexer. So wouldn't it be better to use a not, like RO1 demux and not as the FC?
So just a negation of RO1 demux?
Yeah, because when the RO1 demux is 0, then when it's 0 and then the ALU is enabled, then that means you want to do the increment or decrement. And when the RO1 DMX is a 1, then you don't want to use the constant.
Okay, so let me So you're basically proposing that instead of using, so you're basically proposing the question mark is just R01 demux through a NOT gate. And not use ALU enable as a part of the equation.
Because if the ALU enable is 0, then it doesn't matter what R01 demux is going to be, or the multiplexer that connects to.
True.
So
Yep.
could that also be another answer?
That would be another answer too. But you have to explain that. You have to basically say that if the ALU is not, well, you have to say why it is not affecting existing instructions. Okay, very good. Any questions about this one? No questions? Yep.
So when we're writing out the answer, I mean,
Mhm.
then it's still just saying, oh, connect this to here?
You're just basically writing what I said, but in words. It doesn't have to be complete sentences. It can just be points.
Okay.
Yep. Okay, but in order to answer this question, it really needs you to understand the existing architecture and also all the existing instructions, how the existing instructions are implemented. Is that okay? So now the question boils down to, how do you know how existing instructions are implemented? Okay, let's switch to the page where we see all the instructions. So here's the opcode table of all the instructions, and it doesn't spell out the microcode either. Okay, this one does not spell out the microcode, which determines how the muxes and the demuxes are connecting the components. So how do you know which one is how they're all connected?
Microcode.
The microcode. Okay, so very good. So how do you know the microcode of all of these things, especially in a test when you don't really have a whole lot of time? Okay. For instance, I need to know the microcode of, let's say, the jump instruction. This is the microcode that I need to know in order to answer a question. How do I find it, and how do I interpret that as quickly as possible so that I can say, oh, okay, the jump instruction would involve turning this on, turning that off, and this goes into the input of this demux, that goes into that particular multiplexer, and so on. How do you break it up as quickly as possible? Now, from this table, which I highly recommend that you print out and bring with you to the test, this is from this has an opcode of 1011 is a B. So we are looking at B, and then XX01 is going to be 0001, 0101. Okay, let me just write it down on the other side. Okay, I'm going to write it down first here, and then we'll go back. I'll go to the document that I'm writing here, because I need to copy it first. 1101 XX01. Okay, there we go. All right. So we know the opcode for JMP is like this. This is for JMPX as an instruction. So the next question is, how do you find the microcode corresponding to this particular opcode? Okay, so you make it more specific. So you say 1101 001 0001 is the same as JMP A, because register A is 00. Is that okay? So you have several ways to find this. So this part depends on whether you're kind of more visual or whether you're more analytical. You can go to the ROM, okay? Right click on the ROM. Obviously you cannot do this during the exam, but you can always have a spreadsheet and summarize everything. You go to edit content, and then which location should I go to? Let me switch back to here. We know the opcode is B1. So which location in ROM should I go to locate the microcode corresponding to jump A? B1?
B0.
It's B1. It's B10. because B1 is not going to be able to tell you much. B1 is, this is B1, but B1 corresponds to the second slice of the opcode of 0B, because remember, we have to pad a 0 to the opcode to find its location, the microcode location corresponding to that opcode. So B1 as an opcode will have its microcode specified at B10. So B10 is right here. So let me write it down here. So we have 1 F8 0 0 8 0. Okay. So I just wrote down here bad penmanship because the 8 looks like an F. There we go. All right. So from here we know the hexadecimal representation of all the bits. So we can now spread it out. So we know it's 0 0 0 1 1 1 1 1 1 0 0 0 0 0 0 0 0 0 0 0 0 1 0 0 0 0 0 0 0. Once you have all of these bits spit it out, then you go back to this diagram and you look at this. That's basically what is outputting here. So once you get here, then you go like, where's bit 0 going to? Bit 0 is going to the enable of the instruction register. Okay, so we say this is going to the instruction register enable. And I'm just going to do this a few more times, and then I'll give you the quick answer to this whole thing. Okay, bit 1 is going to RAM select. So we switch back to this diagram and say, this is RAM select, and one more. Okay, this is RAM load. Okay, so we switch back to here and we say this is RAM load, and so on. If you do this during the exam, you won't have enough time, guaranteed. Unless you're a Time Lord and you can change the flow of time. So what do? You don't want to do it this way. You can pre-compile everything, because if you know that this is needed, what are you going to do? What kind of tool are you going to use to help study, at the same time prepare a document that you can bring to the test and go like, I know exactly what is the microcode for this instruction. The assembler manual does not spell out the microcode. It tells you about the effect of the instructions, but it doesn't spell out the microcode. If the microcode is what you need, in other words, you need to know what is going to this, what is going to that, and so on, what is the best way to do it? Okay, let's reverse the question, okay? How did me, end up with how do I specify all of these things in the ROM? Do you think I did it by hand? Or do you think I have a tool to help me? Knowing me, you know that I must have a tool to do this, right? Because I hate tedious work. So what tool is that? Is it available to you? Can you borrow that tool as a help for your test?
Use a spreadsheet.
You can use a spreadsheet. You can definitely turn this into a spreadsheet yourself, but it's already it's already done. What resource do you have? Okay, let's go back to the shared drive, okay? Because everything on the shared drive, I'm hoping people are curious and just kind of poke around and go like, what is this? Okay, here's our shared drive, okay? And we go back to the processor subfolder. And of all of these, has anyone checked out opcodes.zip? No? Have I mentioned this particular folder? No? Okay, so if I have not done that, okay, I might have done that, maybe I just don't, I cannot remember whether I've done it or not. Okay, that's okay. So we'll do, I know I did it for the other class because of the history here, but I don't know whether I did it with this class or not. That's okay. Okay, so when you unzip that folder, okay, I will show you what it looks like. This is the opcodes folder, and I will do a make, oh, it's already clean. This is what it looks like. What does it look like to you?
Instruction programs, C programs.
We have a C program for we have a C file, okay? We have a C source file for each mnemonic that we deal with. Is that okay? Okay, all right, so let's pick one. Let's pick JMP because we were concerned about JMP. Okay, there we go. This is the entire source, this is the entire program of JMP. Okay, so JMP.c looks exactly like this. Okay, do you see a whole bunch of numbers up here? This whole bunch of numbers? They are a part of the array called slices, and I only pass 1 to right slices. Okay, so now the question is, what are these things specifying? Okay, let me get out of here, and I'm going to do it in this mode because it will definitely help you understand what this is for. Okay, these are specific to each bit field of the output of the ROM. This number specifies what is going to microcode pointer reset. This number here, this 1, goes to microcode pointer select. This 1 goes to the next item, which is program counter enable. This number, which is a 7, goes to PC mux. This 1 goes to address mux. This 0 goes to ALU OP, ALU operation, and so on. So why would that be useful to you? Oh, first of all, say for a few names, do you recognize these names? RIEN, register input enable.
Toy processor. They're in the toy processor.
They're in the toy processor as tunnels. Okay. Okay. So what is this telling you? It is spelling out the microcode for the JMP instruction. The way the JMP instruction is implemented has a 0. The first slice of the microcode has a 0 to specify microcode pointer reset. That seems to make sense because I don't want that register to go back to 0. The second one, which is a 1 here, goes to microcode pointer select, which is selecting the mux of how I want to update the microcode pointer. Okay, a 1 means I just want to increment, and so on. So yeah, go ahead.
Is the number to the very left in the bit field?
The middle number?
No, the one on the left.
On the left.
Or sorry, in the right pane. That number.
This is the width of the bit.
Okay, so
this is the position.
on the left, all those numbers. So the 7 is just 3 bits wide. It's not,
Yeah. Yep.
hexadecimal.
Yep. Well, 7 is decimal and also hexadecimal, but it specifies the bit pattern of 111.
Right, but you don't include all 4 bits for it, right? It's just the.
You can specify any number here that specifies the bit pattern that you need. In other words, if you want PC mux to be 2, okay, you just put 2 here,
Right, but
which translates to 010.
But the bit width is 3, so you can't use like F. You can't use anything that uses 4 bits, right?
You should not. I don't think my program guards against that. Okay, but this is spelling out everything that you need. In other words, if you want to know, okay, is a register output 1 demux, used, or what is the value of that thing for the jump instruction, you just have to count. Okay, this is 1, 2, 3, 4, 5, 6, 7, 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. It's a 0. Okay. So is that helping you a little bit in terms of, oh, how do I find out the microcode for a particular instruction, and how do I parse and say, okay, are we using the ALU? If we are using the ALU, which operation are we using? This spells out everything. Is that okay? Let's look at another instruction that can be interesting, and the add instruction. So the add instruction is quite different from the jump instruction, because the add instruction, as you might imagine, needs the ALU, because we need the ALU to perform operations. So you look up on this part here and say, okay, is the ALU enabled turned on? In other words, is that a 1? This is 1, 2, 3, 4, 5, 6, 7. This is the 7th entry from the left. So you go like, okay, 1, 2, 3, 4, 5, 6, 7. It is in, I think I miscounted. 1, 2, 3, 4, 5, 6, 7. That is 7. 1, 2, 3, 4, 5, 6, 7. Yep, it is 7. It is enabled. Is that okay? But the add operation also needs to specify what are we doing with the ALU. ALU-EN is simply saying, yes, we are using the ALU, but the ALU is capable of doing 5 different operations. Which one are we using? It's the one before that, ALU-OP, ALU operation, and that's the 6th entry. 1, 2, 3, 4, 5, 6. It's specifying a 0 to ALU-OP. That specifies the add instruction, or the add path to connect the input to the output. Is that okay? Now what about the XX field, YY field thing? Where do they go? Okay, so let's look at this one here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, the 9th bit field. Count here. 1, 2, 3, 4, 5, 6, 7, 8, 9. It is register output 1 select. Register output 1 select has to select one of the 4 registers, and it corresponds to the YY of the instruction, which is the right-hand side of the registers. Is that okay? So this is helping you. This is having everything kind of parsed already. Yep, go ahead.
Can I ask what's going on with your slices function? What the heck that is?
Which one? Right slice? These 2?
Well, it's calling.
Oh, slices?
Yeah.
Oh, slices is really just this thing. This is a global variable.
It's a global variable.
Yeah, it's a global variable, which is
Two-dimensional array.
It's a 2-dimensional array. Num slices is almost always 2, because we can implement all of the instructions in 2 slices. So that's why num slices is 2, and then we have 18 individual bit fields.
Yeah.
Now there are 26 bits, okay? But some of the bit fields are not single bit, and that's why we have fewer number of bit fields compared to the actual width of the ROM. Okay? Okay, so the bottom line is this is going to be helpful for you guys to study. Okay? You can just print out the C code the way it is, but it's not easy to read that way. So what you might want to do is to use a table. Okay? Use a table, take everything here as columns, and then use individual numbers for each opcode as rows. Okay? So when you do that, you have an easy to look up kind of thing, and you can just easily look up, oh, okay, this is a subtract instruction, and just use X and Y to locate what a particular field is for that instruction. Yep.
What is the second?
Second slice?
Yeah.
The second slice is the second slice of an opcode, and it's almost always the same, because we just need this one here to reset the microcode pointer back to 0. That's how your music box get back to the beginning. That's why the second slice has almost nothing specified except for that one. Okay. So is that okay so far? Now the rest can look kind of confusing. In other words, with one single call, this particular function called right slice is going to be able to generate all 16 variants of the add instruction. 16 variants because the first register has 4 choices of A, B, C, D. The second register also has 4 choices, which is A, B, C, D. So now we have 16 variants. That is taken care of in right slice. I don't think you need to look into right slice to understand how that part works, because you just need to know the pattern to the whole thing, but not specifically how this code works. But this is one thing that can help you with your program. If you don't want to copy everything into your own spreadsheet, you can always just change the program. So instead of right slice and stuff like that, you can make the program just print out all of these individual things separated by a tab. That way you can import that whole thing into an actual spreadsheet. Okay, I know I'm just talking, and some of you are looking at me go like, what are you talking about? Okay, so the way to modify this program, okay, and there's also a kind of cool makefile to this whole thing. This is the makefile, and the makefile, if you just say make, it will compile all of these individual programs, and then the individual programs, each one will take a standard input as an input, and it will crank out the output based on the input. In other words, the input is a .rom file that has all the instructions implemented before this one. And then the program will add its own opcode slices and generate the output. Okay, I can show you exactly how that works. So if we do a cat mt.rom and pipe it to, okay, let's pick CPR. Okay, /. It's this. Because the CPR is compare register, there are 16 variants to the copy register. Excuse me. Copy register is another one where we can steal opcodes from. Does it make sense? Why do you want to copy A to A? Or B to B, or C to C, or D to D? Does that accomplish anything useful at all? Nothing at all. Okay, which means your candidate should be stolen. Okay, so anyway, so when you look at empty.rom, cat empty.rom, this is empty. Empty.rom basically specifies 4,096 locations of zeros in the ROM. Okay, that's filling up the entire ROM with zeros. Okay, but when I pipe empty.rom to CPR, what it does is CPR will first read whatever is piped to it, recreate the entire memory map, okay, with all the content already specified by whatever you pipe in, and then it will run its own code to specify the 16 instructions. And that's what you're seeing here. Each one or each chunk is is one variant of a CPR instruction, and it will integrate the instruction of CPR into whatever is already specified, and it will just spew that out as its output. So you can keep piping these things. Okay, if your processor architecture only needs CPR and LDI instruction, that's the ROM file. So these can stack. Is that okay? So now my question to you is, how do you make use of a set of instructions already like this in order to crank out a TSV or CSV file? So you can just, so the end result is a TSV or tab separated value file that you can just print out and bring it to the test and go like, now we have a table of all the bit fields of all of the opcodes for this entire program. So how would you do that? It's a C programming kind of question. Okay, I'll give you an idea. So I'm going to copy JMP just so that I don't mess up anything in the original one. So we'll do a JMP1.c. So how would you change this program? Okay, instead of read ROM. Okay, now one thing that you may not want to do is to you can always just change what the functions do and not change.
Overload.
Kind of overload, but you're just basically linking it with different things. Okay, so instead of reading the original ROM, you're basically just copying whatever you already have to the output. That's all you're doing. So if whatever is piped to you is already a TSV, a tab separated thing, you can just kind of attach to that. You can just say, okay, I'm going to copy everything that I'm reading to the output, and then I'm going to add my own to the output. Okay, so how do you read everything from the input and just echo everything from the input to the output? You can do it in C, you can do it in C++, but either way, do you guys remember how to read everything from standard input and echo it to the standard output in the regular C program? Yep?
I feel like, there's probably something more efficient, but
Not an array, because you're reading from standard in.
Your standard input stream is C in.
Yep.
And your standard output is C out.
Yep. But how do you copy everything from standard in to standard out?
Good shit.
Not. But what are you reading? Okay, go ahead.
I forgot what it is. I'm trying to remember it.
Okay. Do you know how to do it in C? Regular C.
For scanf and printf.
That's not the most efficient way to do it, but you can do it that way. Okay, but we can do it line by line. Okay, so all right. So we are digressing a little bit here to C programming because this is actually useful to you. There's a function called fgetS. Okay, so you're getting a line at a time. Okay, or you can use character one at a time. So getChar is fine. If you want to use getChar, cool. Okay, use it. But then you have to look at what it's returning. GetChar is the same thing as getC standard in. You're getting one character at a time. Efficiency is not our concern here. So fgetC, which is also getChar, returns the character read as an unsigned character cast to an integer or EOF on end of file or error. Okay. So given that, you go back to JMP1. And you can also, by the way, change ROM. Okay, change how read ROM is defined, and just change that one.
Is that your raw bit?
Huh?
That's from your raw.
That's from microcode.c, I believe. Okay, so read ROM is here. It is defined here. So what you do is you change ucode.c. Okay, you say change ucode.c to ucode1.c, right? And then in here, your so-called read ROM, okay, read ROM, it's going to be something that just echoes everything, all the input goes to the output, right? So you just say while, okay, you need a local character ch here. So you basically say while ch equals to getChar, because we're reading from standard in, so getChar will work. As long as this is not end of file, output. Right, put char, which is the counterpart of getChar. It's just writes it to the output. That's it. You echo everything that's coming into the output. Okay. What about the other parts? Okay. What about the second one, which is write slice? Write slice is really just writing all the slices. For the most part, you don't even have to deal with all of this stuff here, but this is kind of important, which is because this is the actual opcode itself. So the opcode is useful. You might want to add something to give it a name, just so that your table has a name entry corresponding to it. So you might need to modify some of this stuff here. But for the most part, what your write slice is going to do, I'm going to write the code here because we are running out of time, but I just want to give you an idea of what to do. So your code may look like this, okay? You're just basically using for each I, okay, for I equals to 0, I is less than 18 because there are 18 items. And in C, it's basically just a printf, okay, which is, you can see out, okay, in C++, you can use see out. And we'll just say slices, the first slice, the second slice you don't have to output. The second slice is the same for all the instructions, so you don't have to do that. And then for the first slice, this is all you're doing is you need to specify %d will work in this case. So you're basically using a %d, which is printing the value. And then if you are using comma separated, put a comma here. If you're using a tab, put a tab here. So this would generate, multiple things on a single line. Correct. Plus I. And when this is all done, huh? Yeah. The compiler will catch it. There we go. Okay, so here you're basically printing the individual slices or individual bit fields for this instruction. And then the other thing that you might want to do is to print the name of the opcode, just so that it is easy for you to look it up. So you're just basically printing, in this case, it's JMP. Okay, so put that in first. And that's it. That's JMP. So everything that you already have before, you're just copying that, and then you're adding this particular instruction. And you have to kind of do it to every single file that you have. But remember, you can always change how you define BROM. You can change how you define write slice. And then for the second slice, you can just kind of ignore that. And how we know this is the second slice is the last parameter. So the last parameter, if the last parameter is a 0, do something. If the last parameter is a 1, forget it. There's nothing to do. Okay? And then write ROM, there's nothing to do because we are writing the slices as we go. So you can just have a null or just a trivial write ROM. So once you have defined your own microcode.c, I think there's no class after that, so we're kind of safe here. So once you have defined your microcode1.c, you go to the makefile and you make some kind of minor changes. So everywhere you see microcode.o, you change it to microcode1.o, whatever you want to name yours. Okay? So then when you do a make, it would generate a TSV or tab separated value file that you can import into a spreadsheet program. You can reformat the columns to make it look nice and whatnot. Print it out. Now you have a very concise sheet of paper that has all the opcode listed along with the microcode slices in ways that you can easily refer to. So is that okay?
Yeah.
Or not? Cool? All right. So that's going to be something that will be very helpful because you need to know the slices, but you also need to remember how to read this table and map everything back to the processor architecture so that you can say, oh, okay, to implement this instruction, these are the components that we're exercising. Is that okay? All right. So on Wednesday, actually maybe I'll do it in the lab time today. So I will continue to talk about the exam questions today in the lab because we don't have any homework at this point, do we? I don't think so. So I'll just continue to talk about the exam questions in the lab time for people who show up. That's great. Because all of these, we don't have floating point, by the way, okay? Because floating point was in the previous test. So the second exam won't have floating point numbers, but we'll have assembly program. We'll have programming questions. This is the C code. Give me the assembly code. This is the assembly code. Reverse it back to the C code. This is the C code. This is the wrong implementation. Fix it. Okay, so we'll have those questions in this exam.
You say Q5 won't exist?
Yeah, Q5 is not going to be there. But we'll borrow some of the final exam questions into exam 2 of this class. Yep. All right, so I'm going to get out of this classroom and continue this in the lab.
Can I ask you something?
Yep.